This lecture is about carbon-13 NMR. Carbon-13 is a spin-active nucleus. However, the most abundant carbon isotope is carbon-12. The abundance of carbon-13 is only 0.001%. So unlike in a proton NMR, carbon-13 is actually rather hard to see and gives a much weaker signal. To strengthen the signal, we eliminate all coupling, and we can do this by just decoupling, which is an instrument setting. And so in carbon-13 spectra, you will not see any splitting. Carbon-13 chemical shifts range from 0 to 220 ppm. The equivalency is very similar to proton NMR, where you look for symmetry and you can have equivalent carbons. Chemical shifts depend on the environment of that carbon, and we can categorize it according to the functional group. For alkanes, for a carbon that's bonded to only other carbons or hydrogens, the chemical shift is usually between 0 and 45 ppm. If the carbon is an sp3 alkane carbon but it's bonded to a Z atom like nitrogen or oxygen, it gets shifted further downfield and it can be anywhere between 30 to 80 ppm. Alkynes are between 65 to 100 ppm. Alkenes are between 100 to 140. Aromatic carbons are between 120 to 150 ppm. The carbonyl group is generally between 160 to 220 ppm. You should, however, know the subdivisions, so carboxylic acid derivatives are between 160 to 180 ppm, while aldehydes and ketones are further downfield at 190 to 220 ppm. Using what we know, let's try and predict the proton and carbon NMRs for acetone. Acetone has 3 carbons. It's got a ketone at carbon number 2, and it's got a total of 6 protons divided between 2 methyl groups. The first thing we need to do is figure out if acetone has a plane of symmetry, and it does right across here. This implies that these 3 protons are equivalent to these 3 protons, and we would expect only one signal for this molecule. So now we can say that we are going to expect one signal that is going to integrate to 6 protons, and if it's equivalent, we know that they're not going to be splitting each other, and so we have a singlet, and the assignment are these methyl protons, so 2 times the methyl protons. And now let's predict the chemical shift. We know that alkane protons are going to be fairly upfield and very likely in the 0 to 2.5 ppm range. Now let's look at what's next to this carbon. Next to this carbon is an electron withdrawing group, the ketone, and so we can predict that these protons will be closer to 2.5 than to 0. So we would predict it around 2.0 ppm. And in reality, we would be quite right. It comes up at 2.18 ppm. Let's do the same thing for the carbon NMR. We already said that we had a plane of symmetry down here, which means that if we label these carbons 1, 2, and 3, carbon 1 is equivalent to carbon 3, and we will expect a total of 2 signals. So we know that carbon 1 and carbon 3 are going to be the same, and we should have a separate signal for carbon 2. Carbon 2 is a ketone, and so we can look at the table and we know that ketones are going to come between 190 to 220. So we can predict it around 200 ppm. And if we had to integrate it, it would come up to 1 carbon. The remaining 2 carbons are equivalent, and those chemical shifts are going to be between 0 and 45 because they are simple alkane carbons. And remember again, since they're attached to an electron withdrawing group, it's probably going to be closer to 45 than to 0. So here we would expect it maybe around 30 ppm. And in reality, the chemical shifts are 33.1 ppm and 206.0 ppm. A final note about integration. we almost never integrate a carbon NMR, and that's because if you took the carbon NMR of this compound, this peak would not be half the height of this peak, even though this has half the number of carbons as this peak does. And that's because a CH, CH2, CH3 all have these hydrogen signals feeding into the carbon signals due to decoupling. A quaternary carbon is going to be a very weak signal because it has no hydrogens feeding into it. And so it's hard to predict how high these peaks would be and how much it would integrate to. So we would be able to compare, for instance, a methyl to another methyl, but comparing the height or the integration of a methyl to a methine or a quaternary carbon is not going to give us any accurate results.